All right, so let's get started. For those watching online, we have technical problems, so we're going to have to just film the screen. So you won't see me as much. First, I have an announcement from Kimmy here.
Okay. Oh, here. Hey guys. So as many of you know, I am one of your awesome TAs, Kimmy. I'm also a general officer for the Crimson Gaming Club. Your home for gaming on campus. And this Saturday, December 1st, we're going to have a big event called Crimson Land, where everyone comes together, plays games, competes in competitions, and get cool prizes, which is awesome. So it's going to be from 9 a.m. to 5 p.m. in Building 72, which is by the new law building and stadium. And you will have to pay $50 at the door to get in. But in the process, you will get a raffle ticket to win awesome prizes. For our last raffle, we raffled off at 1080, which if you don't know what that is, that's about $500 to $600 online. So if you don't know what it is, you just sell it. So for the event, we're gonna have a ton of games. We're gonna have Tekken, we're gonna have Street Fighter, we're gonna have Melee, we're gonna have Smash, we're gonna have Fortnite, League, and all these cool games. We're also having Hearthstone, which I know a lot of you guys like this. You guys are always playing it in the back. So, be sure to go to this link here. This is the Facebook event page where you can sign up for your tournaments. And you will have to sign up the night before at least, because it closes out after Friday. So be sure to go here. Remember, go here. Say you're going, so you get an extra raffle ticket when you come to the door. And yeah, so I hope to see you there. And awesome.
Okay. Today I'm going to show you that you can do computer science without computers, without programming. There's a famous saying by Oscar Dijkstra, a famous computer scientist, that said computers have as much to do with computer science as telescopes do with astronomy. So the idea being that computers are a tool to study computing. They're not necessarily the focus of computing. What we're going to talk about is sorting, putting things in order. So it turns out to be a really important problem in computer science. So think about your phones, your laptops. Where are things sorted? Anything on your phone sorted? When you use your computer, do you see things in some order? Yeah? Okay, songs you sort by name or by artist or genre, whatever. Okay? Yeah?
Most files are sorted.
Okay, when you go browse your files, you can get an alphabetical order or order of size or order of date created, stuff like that. Yeah?
Contact lists.
Contact lists are sorted. And you go use Excel, you sort columns, sort rows. So sorting happens all the time, and it's not just important because people like to see things in sorted order. It turns out that a lot of algorithms that do things fast, internally they sort something before they use that something. So you can't turn around on a computer without encountering sorting. It turns out also that sorting is a major topic in 2420. So I'm not going to cover everything that there is to know about sorting, but I'm going to introduce you to the idea. So to get our feet wet over here, I have these 8 cards on the chalk tray, and they each have a number written on the back. So I want to put them into ascending order from left to right. Okay? And I'm going to have you do it. You help me do it. You just got to tell me which ones to swap. So that's one operation you have. You can tell me to swap. I guess I should label them. So this is A, B, C, D, E, F, G, and H. So you can tell me to swap a pair. Is that enough to do sorting? If that's the only power I give you, is tell me to swap, like you said, tell me to swap F and H. What's missing?
Comparison?
The what?
Like to compare?
Okay, also need to, you don't know what's on the back. So you need to, you can also ask me, is A less than F? Okay, so those are the only two things you can do. You can ask me if one card is less than another, and you can ask me to swap a pair. And so to do it, you've got to have a sorting algorithm to basically run in your head. So who'd like to give it a try? Okay. Okay, is B less than A? No. Is C less than B? Yes. Okay. Swap C and B. Okay. Is B less than A? No. Is B less than C? Oh, is B less than D? Oh, is D less than C? Yes. Okay. Is C less than E? E. You need my microphone.
Yeah.
Okay, say it again.
C is in Charlie and B is in.
No. C is not less than B.
And is E echo less than E delta?
Yes. Echo is less than delta.
Then swap.
Okay, let me interrupt you for a second. So, have you caught on to what he's doing yet? What's he doing? Yeah.
Insertion sort. Well, he's essentially moving things back into this until you know that they're over
Okay.
below or less than.
So you say he's doing insertion sort. Is that what you're doing?
Well, it's like, yeah, it was like the second one in the.
Okay.
Insertion sort.
So we could play this game out, but the idea is you do sorting by comparisons and swaps. So at this point, what are you confident of? How sorted is this up here?
It's like A through E.
Okay, so if he's done things correctly, A through E should be in ascending order. Because,
I don't know if E is, I think D is.
okay, so maybe ask me if D is less than E, and it is. Okay, so let's see how we did. So we got a 1 here, a 4, a 7, a 5, and an 8. Okay, so it had a small staff loop, but communications were difficult. Okay? So that gives you an idea of what a sorting algorithm has to do. It just does comparisons and then moves things around in response. So let's look at one on the screen up here. So what I have here, this allows me to animate sorting algorithms. So let me explain what you're looking at. Imagine that this is like a two-dimensional plot. Along the horizontal axis, that's an index into the array being sorted. So if you think of, these are lettered A, B, C, D, E, F, G, H. Think about that as going along the bottom row. So along the bottom row is array indexes. The x-axis is array indexes. The y-index is the magnitude of the things in the array. So what this says here is that, let me make the size smaller. Okay, this says index 0 contains 0. Okay, so this is, okay, so what's in index 1? 1. Index 2 contains 2, index 3 contains 3. So to tell what an index contains, you just count how many squares up it is. So this one is 0 squares up, that's 1 square up, that's 2 squares up. This one is up here is 7 squares up. So what would it look like if it were in reverse order? This is ascending order, this is sorted in ascending order. What would it look like if it were sorted in descending order? It'd just be going the other way. So I can do that. So that's what descending order looks like. So we've got the biggest thing first and the smallest thing last. Okay? What's that? Right, well, it's unsorted. We'll call that's just a permutation. That's a possible permutation. It's some way you could randomly mix up the elements. So if you think about this as the numbers 0 through 7, what's at index 0? Right? We got a 7 and then what? A 6. That was 0, 1, 2. So that's 2, 1, 5, 4, 0, 3. Okay? And the cool thing is that you can, the nice thing about this is that when it is sorted, it's clear. All right, so let's start by looking at selection sort. Okay? That's different from what we were doing before. The way selection sort works is we search through the entire array and find the smallest element. And once we found the smallest element, we plop it into column 0. Because clearly that's where the smallest element belongs. Then what do? Right, now we said find the next smallest element. And the way we do that is we ignore column 0 because it's done. Now we just focus on columns 1 through 7. Find the smallest element in it, put it in the first column, and gradually the area of uncertainty shrinks. So let's step through this. So what will happen is when they flash red, that means they're being compared. So right now the selection sort is comparing the first two elements. And it's going to discover that this one here, the one in column 0, is the smallest. So when I hit step again, now it's comparing this one, that's the smallest one it's found so far, with this one. And of course now this one is the new champion, one at the bottom. So if I say step again, it's going to compare the 0 to 2, and then 0 to 5, to 4, to 7, to 1. And at that point, it knows that this one here is the smallest one it found. So it's done those 7 comparisons. What's it do now? It's going to swap. It wants to put the low red one in the first column. And so it's going to have to move the thing that's in the first column to the second column. So it's going to swap these two.
Third column.
Okay. Now it's going to go through and try to find the smallest. It's going to step through the rest of here. It's found the new smallest, and it swaps it in 2 steps. We're seeing the swap happen in 2 steps. Then it compares, it looks for a new champion, swaps it in place. Looks for a new champion. Turns out it was in the right place anyway. And now it's going to do it. You're not going to see anything change because it was already ordered. So that's how selection sort works. Yeah.
Oh, this is selection sort?
Yeah. Now, let's run it. So I'm going to permute it again, and let's just run it and watch what happens. Now, that's not very revealing, is it? So let's increase the size. I'm going to increase the size up to 256. No, that's not going to work. The trick is to keep it square. And we'll resize. Okay, so that's pretty good. I'll do that. You can't quite see the bottom. Okay, and I'm going to put the speed on moderate. So we'll slow it down a little bit. And I'm going to click start. Oh, I'm going to click permute first. Now, what are you going to see? Just you see this sea of scrambled dots. Now you know when it's done, it's going to be perfectly sorted. That diagonal line. What's it going to look like as it's being sorted? What's the animation going to look like? Yeah. Okay, he said a line is going to grow from the lower left-hand corner because it continually puts the correct thing all to the left. So what you'll see, let's see if I can expose the bottom there. This is want to go up. I'll just make it smaller so you can see everything. Let's just run it and see. So it's, it takes a while because I've slowed it down with some delays in there. And you can't really see the red comparisons happening because they're so small. But it's just each pass through, it's sweeping through, finding the smallest, swapping it into that column. And so the effect you get is it's growing from the bottom and the area of uncertainty is shrinking. So is this line going to grow faster or slower as the sort proceeds? It's going to get faster because the area that has to search through each time is smaller by 1. And you get the idea, so I can speed it up. Okay, so that's selection sort. Is that a good algorithm or a bad algorithm? It's one thing to understand an algorithm. The other thing you have to do is evaluate it, compare it to others, decide is it any good, is it, there has to be some way to compare algorithms. So let me give you an inkling about that. You'll study in 2420, if you take 2420, you'll learn about algorithm analysis. And we don't have much time to do that here, but I can give you a visual idea about what algorithm analysis is like. You look down here at the very bottom, you'll see that it did 32,640 comparisons in 510 stores. It stored something into it moved something that many times. So it turns out that when trying to understand sorting algorithms, try to understand their efficiency, we really can just pay attention to how many times it does comparisons. Now, why does that make some sense? Why can we ignore everything else if we're trying to get some idea of how efficient an algorithm is for sorting? Why is it okay just to count how many comparisons it does? Yeah? All right, you said that's the vast majority of what it does. You're not going to find a sorting algorithm that does 1 comparison and then it does 10 swaps. The sorting algorithm is going to do a bunch of comparisons and relatively fewer swaps. So the time it takes for a sorting algorithm to run is dominated by the time it takes to do the comparisons. So we'll focus on that. And I can do this visually rather than just numerically. So I'm going to do this. I'm going to have to shrink it. No. I'll go back. I'm going to go down to 128 and then shrink this down a bit. Okay. So, well, let me do it this way. Let me just run this through. I'll explain what I did. So this bottom plot shows comparisons. And we know that selection sort sweeps through the array and finds the smallest, and then sweeps through the array and finds the smallest, and so on. So as you come down from the top in this bottom display, that first line shows all the spots in the array that were involved in comparisons during the first pass. So what does that tell us? That first line goes from one end to the other. And every element was looked at on the first pass through. Okay? What happened on the second pass through? Right? All but the first element was looked at. And then all but the second element was looked at. So that, you see each pass there were fewer comparisons to make. And we saw that when we animated it. So let's go back to 64 here and commute it. And I'll slow the speed down again and we'll start it. So it's filling in everything that's involved in a comparison in each pass. Okay? Now, looking at that graph right there, we can come up with our first theoretical result about sorting. How many comparisons, how many comparisons does it take if you're sorting an array of size n? Yeah. Yeah, he said n squared over 2. So where did that come from? Who could tell me where that came from? Yeah.
Well, it looks like the area of the triangle would be
Okay, it's an area of a triangle. So that's base times height divided by 2. And the base and the height are each n, if there's n elements in the array. So that's 1/2 n squared, or it's half of the square, 1/2 n squared. So it turns out that that's about all there is to algorithm analysis, is figuring out how the running time, is, at least for analyzing sorting, is figuring out how many comparisons there are as a function of n. So let me come over here and I'll do it here. So we just decided selection sort does about 1/2 n squared comparisons. Now we could, I think it may be like 1/2 n minus 1 squared or something, but that's close enough. So let's make a prediction. It did about 2,000 comparisons in sorting whatever this was, 64 elements. What do we expect to happen if we double the number of elements? Let's do a little math. So it did 1/2 n squared comparisons when we did n. How many comparisons would we predict for 2n, if we double n? Yeah.
4 times as many.
Yeah, 4 times as many. The formula then would be 1/2 2n squared. And the 1/2s cancel. We end up with 4n squared over n squared, and that's 4. So we expect the number of comparisons to increase by a factor of 4 when we double the size of the array. And the technical term for an algorithm that has that behavior, whose running time quadruples when the problem size doubles, is an O of n squared algorithm. Technically, it's a theta of n squared algorithm that will be a little bit imprecise, and just call it that. So if you've heard that you're going to learn about big O notation in 2420, that's what it is. It's just sort of a very imprecise count. We're just saying that the running time of selection sort grows at the same rate as an n squared function. Let's see if our prediction bears out. So it did about 2,000 comparisons. If I double, I should get about 8,000, right? There we are. Now, does this result matter? Well, okay, I didn't mean to stop there, but yes, this result matters. It's important to know. Does it depend on what kind of computer you're using? If you ran this animation on your computer, would you get the same number of comparisons? Sure. The animation might run faster or slower, but the number of comparisons would be the same. So another thing about big O notation is it gets us away from having to worry, we don't, it's hard to talk about efficiency if what you're talking about is how long the program takes to run. Because everyone's computer runs at different speeds. But it's going to be constant how many comparisons. That's going to be the same on everyone's computer. So it's sort of a portable measure of the efficiency of the algorithm. Okay, let's compare it to a different algorithm now. And now I'm going to do insertion sort. So I'm going to set the size back to something small like 8. And who could explain how insertion sort works? You saw it acted out in front of you, but yeah.
So we can sort of consider the first element in the list where we sorted because it's just one.
Okay.
So if we just think of it as the sorted portion and the sorted portion. So we're going to take the first element in the unsorted compare it to see if it's greater than or less than
Mhm.
that element. And if it's less than, we'll swap and we'll move it there.
Okay.
And if not, then we'll leave it. And then, we'll know that that portion of the list, those two elements are sorted. So we'll do a similar thing for the third element. We'll compare it to the second. If it's smaller, then we'll swap it. Then we'll, and if we swap it then we'll compare it again. And if it's smaller, swap it.
Okay.
Just so on through the entire list.
Okay, so what he said is correct. The idea is that we don't even worry about the first element. We look at the second element here. And we try to push it as far to the left as we can. We move it as far as the left as we can until we either get all the way to the left or until we run into something that's smaller than it is. So if we try to push this first the thing in column 1, so column 0 is sitting there, the thing in column 1, if you try to push it to the left, what's going to happen? It'll find something smaller and swap places with it. So let me step through here. We compare those two and exchange them. Now, the first two elements are in ascending order. They're not necessarily where they're going to be in the final result, but they're where they belong right now. Now we're going to look at at this column. We compare those two. What's going to happen? You know, they're in the right order, so no swap will happen. So then we will turn our attention to these two. Now, this one is smaller than that one, and smaller than the next one, and smaller than the last one. And so we're going to see it gradually be pushed to the left. So I'll always step, step, step. Okay? Now we compare those two. Nothing will happen. We compare those two. Nothing will happen. We compare those, and this one is going to make its way all the way to the bottom. And then finally, we'll push this one as far over as we can. And we're done. So that's insertion sort. So if I use a bigger size, like 128, and permute it, what do you think this picture will look like? What will this animation look like as it runs? Yeah?
It's going to be kind of linear as it first starts growing, but it's going to kind of wiggle a little bit as things are inserted, and then it's going to start looking more linear.
Okay. So yeah, very nice. So again, just like with selection sort, there'll be the left part will be ordered, but not perfectly. We said a wiggly line. Those are the ones that we put in the correct relative order. And then there'll be the unknown section that's sorted randomly. And so the area of organization will gradually move. So I'll slow this down so you can see what's going on, and we'll hit start. So what you're seeing as motion is just the elements being shoved down to their right place, being moved to the left until they get to their right place. So the wave sort of propagates down. And if you'll watch, when we get here, this to the least element, it'll take it'll take longer to propagate down. It's about ready for it to go. So there it goes all the way down. Now this gets slower toward the end, right? So it's the opposite of selection sort. Okay. So you think this is better or worse than selection sort? How could we approach it? Yeah? Well, yeah, if you look at, it is doing more stores than selection sort. That's true. Our gain is only to look at comparisons. Yeah?
Yeah, if you only look at comparisons, it's doing less comparisons, so that should mean that it's a little bit better.
Okay. Well, what we did before was we looked at comparisons, so let's do it graphically again. So I will go, I think last time we did the experiment was 64. And I will come here and turn on the code that shows comparisons. And let's permute, and let's run it. So let's understand what we're seeing. Each row from the top to the bottom is dealing with one element, pushing it as far left, and then the next line is pushing the next one as far left as we can. Why are some, like this one here, is black all the way over, and this one here doesn't last very long? What's that an artifact of? Yeah.
Depends how far out of place it was.
Okay, depends on how far out of place it was. Remember, I told you to pay attention to one of them that was going to be pushed a long way over. So the ones that have to be pushed a long way over end up doing more comparisons, and the ones that don't have to be pushed do fewer comparisons. So just looking at that. In fact, let's go up to 128. And put it on fast. Okay, so just looking at these graphs, which algorithm does more comparisons? Selection sort or insertion sort? Right, insertion sort does, because fewer comparisons, because with selection sort you have a solid wedge, right? A solid half of the square. And here we don't. It turns out that selection sort doesn't do the same number of comparisons every time. So that's very typical of a random situation. What would happen if I sorted this straight line? What if I sorted it? What if I just click start right now without permuting it? What will the comparison plot look like? It'll just be a straight line too, because we only do one comparison for each element, because it's already in the right place. So let's do that. Turns out insertion sort is really fast if the array is sorted or almost sorted. On the other hand, what if you got so unlucky to get something that's sorted in reverse order?
Yeah.
So in that case, we're actually, it's the same number of comparisons as selection sort. Of course, more swaps, so more expensive. So this gets into another aspect when we learn about algorithms. You're sometimes interested in the best case, the worst case, or the average case. So on average, how many comparisons would you say that insertion sort does on average, if you've got n elements? Let me give you a picture to look at. It's less than half n squared, yeah? Well, half n squared would be if everything was solid block.
Oh yeah, half of that.
Half of that. So it turns out that insertion sort, on average, is 1/4 n squared. But it's still, we say it's O of n squared. Even though, by this measure, it's twice as fast. So why is it the fact that, even though it's, does half the comparisons, why do we still call it O of n squared? Yeah.
We're interested in like the long-term growth patterns.
Right. We're interested in the long-term growth patterns. We're interested in what happens when you double the size of the input. So if you double the size of the input for insertion sort, you can do the same math. You just have a 1/4 here, and they'll cancel out just like the 1/2 did. You're still going to find out that double the size of the input, insertion sort takes 4 times as long. That's what an n squared algorithm is. Okay. Now back to selection sort. Does it have worst and best cases that are different, the way insertion sort does? Let's see. Let's permute that. Go to selection sort. Okay, we know what that looks like. We get half it shaded in. But what if I sort something that's already sorted? Same thing. If I sort something that is in reverse order, picture looks different, but the number of comparisons is the same. So selection sort is equally bad for all input sizes. I once asked on an exam what would be the best algorithm sorting algorithm for sorting elephants into stalls. Because that's the only good application for selection sort I can think of. Because it does as few swaps as possible. So just imagine that you compare the elephants in some way, and then you just lead it to the next stall. Now, is this the best we can do? You see a pair of n-squared algorithms here. Okay. I'm going to show you, turn this off so they have more screen real estate. Make this big. I'll make the size be 512. Now it's not big enough. 256. I'll permute it. And I will, let's see, I'll put the speed on fast. And we will sort using insertion sort, which is our current champion. And let's just look at it and let's see how long it takes. Okay, that's our n-squared algorithm. Now let's permute it. And let's use a different algorithm like merge sort. Okay. Or quick sort. Those algorithms are not n-squared, they're faster. Let's take a break and we'll see how merge sort works. All right, let's get going again. So as algorithms get more, as these sorting algorithms get more efficient, they get harder to explain, especially with these pictures. But fortunately, merge sort is pretty easy to explain just using these cards here. So let me explain how merge sort works. You split the array in half. So we're going to split the array into, these cards are so flaky I don't want to divide them too much. But just think of this, we've split the array into this half, into that half. Then you sort the two halves. So I'll sort this one here. They weren't thinking of me when they did this. Okay. Okay, so you sort the first half.
Why don't you get 8 people to hold it?
You sort the second half.
8 volunteers.
Sure.
8 volunteers, come down.
That's the hard part.
Okay.
Now each pick up a piece of paper.
This is 6.
Just put yourself in some random order.
One more.
One more. Oh, there it is.
I got one more thing to add to my list of complaints about this room.
No.
Okay. So what I do is I split it in half. So you 4 sort of go over there. And then sort yourself. And while they're doing it, why don't you sort yourself too?
Which way is the big side?
Yeah, we're going, okay. So we've just sorted the two halves. And now we merge. We know that this set is sorted and this set is sorted. And so we're going to combine them into a single array that's also sorted. But we can do that very efficiently. Because of these two, if you weren't looking at the numbers they're holding up, who are the only 2 people who could be holding the smallest number? All right, it's the person on the left end of their group. So to merge, we just, okay, now I'll show you numbers. To merge, I just look at the leftmost person, and the leftmost person, you're the smallest, so you come stand here. So I'm putting him in a new array. Then 2 and 3, 2 come here. 3 and 6, 3 comes here. I compare the 6 and the 4, 4 is smallest. I compare the 5 and the 6, 5 is smallest. And then if one array is exhausted, then I just copy them up. So 6, 7, 8 come up like this. So I just had to make a single pass through the 2 arrays to merge them together. Yeah?
What if, like, if 7 and 8 were out of order? Oh, I guess it would compare.
Right, 7 and 8 had to be in order because they were in the same subarray, which was sorted. Yeah? How do you sort the 2 arrays that you split in half? Anyone have an idea? Could we sort them with selection sort?
Yeah.
Sure. But why not use insertion sort? That's faster. We could do that, couldn't we? Sort the 2 halves? Sure. Yeah? We could use merge sort. Very good.
He has a question.
Merge sort is recursive. So you sort the 2 halves using merge sort.
Your array element has a question.
Yes, which array element has a question?
That was my question, actually, is whether or not it's going to do its, yeah.
Yeah. So merge sort, you don't really see it when you look at the animation. Can't really tell from the animation, but it's recursive. You just use merge sort to sort you split, then run merge sort twice, sorting each half, and then do the merge. Another nice thing about merge sort is it's easy to parallelize. Suppose you had 2 cores in your computer. You could sort one half on one core while you're simultaneously sorting the other half on the other core. So that's another thing about algorithms is you worry about whether they can, can you make them run in parallel? Okay, hand me your cards and you can go sit down. Now I'm going to show you an animation of merge sort, but it works a little different. To get the animation to work, it's a little different the way I just described the algorithm. So what it does is it doesn't physically split the array in half. Merge sort takes a parameter that says sort this array from index something to index something else, and it sorts what's in between. So you split in half by using the indexes. But when it comes time to merge, what it does is it merges, when it needs to merge two elements over there, it merges them, or two subarrays over there, it merges them into this extra array over here. So this is a currently empty array. And then once they're merged, it copies them back. So unfortunately, you can't merge in place. You've got to make a copy somewhere. I'm just making the copy after I merge instead of making the copy before I sort. So I'm going to step through this. Tell me, which of the first two elements will be compared by merge sort? Because conceptually, it's going to split the array into half. So it's going to sort the first 8 elements here with merge sort. And then it's going to sort the last 8 elements with merge sort. And then it's going to merge them. But what's going to happen when we go to sort the first 8 elements with merge sort? It's going to split them into groups of 4. It'll sort the first 4 elements. And what's going to happen when we merge sort the first 4 elements? It's going to merge sort the first 2 elements. And so the first 2 that are compared will be these two, the 2 on the left. So we'll step through it. So those get compared. And they get merged over there. And then they get copied back in the right order. So those 2 get compared, they get merged. Actually, what you're seeing is the only comparisons occur in the merging. So now we have these first 2 elements are sorted and these next 2 elements are sorted. So we're going to sort the first 2 with the next 2. Okay? So we merge those and then they get copied back. Now we're going to proceed to sort the next 4, which is going to involve several steps. So like I say, this animation probably isn't the best way to understand what's going on. But now we have the first 4 in order and the next 4 in order. And the next thing that will happen is those will be merged. Those 2 sets of 4 will be merged. And it gets copied back. And then the same thing will happen with the rest of the array. So I'll go through that pretty fast. And at some point, you're left with 2 sorted partial arrays. And what's the last thing that happens? We're back at the top level where we sorted the 2 halves. Now all we got to do is merge them. And the merging happens in the other array. And then it's copied back. So that's merge sort. Let's run it at speed so you can get an appreciation of what's going on. So let's go to a size of like 256, permuted, speed, I'll make it moderate because it's so fast, and then say start. So when you see things flash over here, it's because it's in the process of merging. So like when I did a merge and asked them to step to a different part of the room, it's equivalent of merging and putting your result over here before you copy it back. Okay, now you can see the final merge happening, and then the final copy back. Okay? So that is merge sort. Now, it looks a lot faster. I showed you before the break. It flies compared to selection sort. But we need to do a little analysis here. So what's our technique for doing analysis?
Run it when it's already sorted.
Say it.
Run it when it's already sorted.
Well, yeah, we can compare worst and best cases. But let's do that right now. So it's already sorted. Let's see what happens. Yeah, it doesn't seem to be taking any particular advantage of the fact that it's already sorted. There's not much to look at, but it's discovering that it's sorted. And the final merge happens. Now, if we reverse it, it's kind of cute to look at. also had exam questions in my algorithms class where I would put stills of these animations on the exam and say, what algorithm is this? Because it's really characteristic. Okay, but what did we do to decide that these two algorithms were n squared? Well, the first thing we did was we looked at comparisons. We looked at a comparison graph, right? So let's do that. So I'm going to take the extra array away so we don't see it. And we'll put the comparison graph up. And it's hard. Okay, let me make it smaller. So everything fits. Okay. Now, what you're going to find out now is, well, let me run it once and I'll explain what the graph looks like, what the graph is for. So here we go. So again, it's showing you which two elements have been compared. But what did you notice when I did that? Let me slow it down. In what order did things get filled in? Sort of working from the bottom up. So the top row, the top line of this graph here, corresponds to the comparisons that were done at the top level of the method call. The next line is what happens one level deep in the recursion. What happens 2 levels deep in the recursion, and all the way down. So the top line is when we were sorting an array of size 64. The next row is 2 times we sorted arrays of size 32. Down below is 4 arrays of size 16 were sorted, and so on. So given that, look at that and tell me, what conclusions can you draw about how many comparisons insertion merge sort does? Yeah?
Like the log base 2 of
Okay. You're going to do well, 2420. Okay, so the first observation is, this is pretty much a solid rectangle, right?
You didn't repeat what he said.
Well, because I'm going to
Intentionally.
I'm going to tell you what he said a different way. Now, just to make sure let's just do a couple more. So let's sort that. I'll put it on fast. Again, it's almost completely filled in. It's almost completely filled in. What do the gaps mean? Where are the little white squares coming from? Yeah?
You didn't have to do a comparison.
That's when we didn't have to do a comparison. Now, when does that happen, that you didn't have to do a comparison? Yeah?
When one of the 2 arrays is exhausted.
Right, one of the 2 arrays was exhausted and you get to move for free. So you remember when we did that, there were 3 people left over when the first array was exhausted and they all got to be copied over. The last 2 were never involved in a comparison. So if, let's see if I can make it solid. No, the other way. Okay, I'm not, that's, okay, I can't make it solid. That's pretty solid. So let's just say that on average, that you get a solid rectangle. Now, how far across is it? If you're sorting in elements. Yeah. All right, so it's n wide. Now, it's not n deep. What he said was the depth is the log base 2 of n. Now, I know people go heading, running for the exits when they hear log base 2. So let me just write that up here. No, it's not selection, it's merge. We're saying it's n times the log base 2 of n. What determines the depth, the depth of that thing up there? Yeah.
How many times it has split?
Right. How many times can you split the array until you get just a single element left? So if you start with 64, The next level, so that's one level. And the next level, you're sorting 2 arrays of size 32. The next level, arrays of size 16, 8, 4, 2, 1. Now, but the point where you're sorting arrays of length 1, you do no comparison. So there's 6 levels. How many times can you divide 32 by 2, or I'm sorry, 64 by 2 before you get to 1? So let's see, 64, I divide it by 2, I get 32, 16, 8, 4, 2, 1, 6. Log base 2 of a number is just how many times you can divide it by 2 before you get to 1. So that's the complexity of merge sort, n log n. Turns out the base of the logarithm doesn't matter. The base of the logarithm has the same status as the 1/2 or the 1/4. We just say that merge sort is O of n log n, which is a lot better than n squared. Okay, let me show you another one. Quick sort. So what do you observe here? How does that compare to the picture we got for merge sort? So I haven't told you anything about how quick sort works, and I'm not going to. But just look at that picture and tell me, how is that qualitatively different? The comparison plot at the bottom. How is that qualitatively different for merge sort? Yeah? The depth is ragged. It's not a constant depth. So sometimes, I'll just take quick sort's recursive. Sometimes the recursion dives down deeper. Sometimes shallower. What else do you see? Yeah?
It's almost all filled in.
It's almost all filled in, but you might argue there are more gaps. I'm not sure. Quick sort is also n log n, but in practice it's faster. The same way insertion sort is faster than selection sort. Quick sort can be twice as fast, say, as merge sort. There's a theorem that says you can't do better than that. That if what you're sorting, if all you can do when you sort is compare elements and move them around, you can't do better than n log n. That doesn't mean you stop looking for better algorithms, because merge sort and quick sort are both n log n, but one's faster than the other. But you're not going to have a massive breakthrough like when you go from insertion sort to merge sort. So just to drive this point home before I'm done with this animation, I'm going to get rid of the comparisons and make this thing as big as I can. 512 elements. You can almost see them all. And I'm going to permute it and sort it with selection sort. That's an n squared algorithm. It's running flat out right now. Now, this doesn't mean that a real selection sort would be this slow in such a small array. Why is this slow? It's all the graphics I'm doing. You don't typically animate your sorting algorithm. So that took a while. Now let's compare that to quick sort. Okay, that's the difference between n squared and n log n, and that's the reason we study algorithms. Okay? Now, I want to end here by showing you a little bit of code, even though I said we wouldn't. You could learn about algorithms without doing programming. You've got to do a little bit of programming anyway. So this is an implementation of selection sort, a little bit of code missing. So what I have down here is a method called index of smallest. You give it an array and an index to start at, and it will give you back the index of the smallest element between I and the end of the array. So let's use that up here to implement selection sort. So we got a loop written for us already that's moving through the array. And each time through the array, what are we supposed to do? Right, we want to find the index of the smallest. Okay, and where do we start looking? Right, we start at I and we go to the end of the array. I need to do A first. So that's, right? So you start at I equals 0. So at first pass, you're looking from 0 to the end of the array, the smallest index of the smallest element. Next pass, from 1 to the end of the array, 2 to the end of the array. What do you do with this index? Yeah. Okay, you swap it with I. And I have a method down here that'll do that, swap. So I just say swap what's at index I with what's at this new index we just discovered. And I have to give the array to first parameter. All right, so there is selection sort. Now we can find this. I'm going to do a timing experiment with it. So what this does is it starts with I equal 1,000 and then it doubles each time until it gets to 1,000,000. So it'll create an array of length 1,000, permute it, sort it, and see how long it took. And then it'll do 2,000, 4,000, 8,000. The timing code that I'm doing here is really not very good. If you take 2420, you'll be doing experiments like this. You heard that you write code and do experiments and write reports. You basically be timing things and comparing. This is a really cheap, I don't want you to tell the 2420 professor that I said this is the best way to time algorithms. This is just meant to be simple. It's just, so let's run it and see. Okay, so what we're seeing is how much time it takes. So it took 4 seconds. How much time will, the next array will be twice as big. How long will it take to run? How much longer than 4.6 seconds? 4 times longer. So it ought to be about 18 seconds. So our results are reflecting our theory. The next one will take over a minute. Now, the number in the third column is the ratio between the, like 0.52 is a ratio between the number for 2,000 and the number for 1,000. Now, you may wonder, why were we able to sort an array of length 2,000 faster than 1,000? It's because my timing code is really sloppy. I'm not going to go into the details, but I didn't do a very careful job of timing. But how do those numbers settle down over the long haul? The ratio is, what ratio would you expect in theory between each line you're doubling the size of the array? Yeah? 4. Right? It's supposed to take 4 times as long. And we see that, and if you keep going for bigger and bigger numbers, it'll gradually settle down really close to 4. Okay? But I'm not that patient. Now, let's look at merge sort. And again, I've got a lot of code written. Except I can't. Just to drag down. Okay. So we're going to use the algorithm we use with the people. So what I'm going to do is I'll take the array that first of all, I've got this if. If the length is greater than 1, I do something. What if the length is 1 or 0? We're asked to sort an empty array or an array of length 1. It's already sorted. So we do nothing. Otherwise, what we do is there's a built-in method called copy of arrays. It'll take, what it does, it takes A and it goes from index 0 to A dot length divided by 2 minus 1. And copies it out into a new array and returns it. So left is the first half of the array, right is the second half of the array. What do I do to complete merge sort? I have the 2 halves here. What are the first 2 things I need to do? Right. I recursively sort the left half, I recursively sort the right half. Now left and right are sorted. What do I do with the two sorted halves? What do we do with the sorted people? We merge them. And fortunately, there's a method merge right here. So I'd say I want to merge this array with this array and put the result back in A. And that's a merge sort. Okay, let's time it. So let's look what we did down here. So we got up to 256,000 before I lost my patience, and that took 18 seconds. So we'll come here to the sort timer. We'll, instead of timing selection, we'll time merge sort. So let's run it and see how long that takes. Oh, I ran it to 10 million, not a million. But anyway, before I even looked at it, we've gotten past where I lost my patience for the other algorithm. Now look at the ratios. Again, 2,000 was faster than 1,000. Anyone got a theory for why the second test runs faster than the first test, even though it's bigger array? Yeah?
Maybe there's a flat time cost for timing or something like that?
Well, he said maybe there's a flat time cost for timing. There's basically a flat cost for running a Java program. Things have to get loaded and initialized, and we're sort of paying that price in the first timing. So that's one thing you need to not, that's what you learn about 2420. Anyway, it's sort of settled down. Suppose it weren't n log n. Suppose it was O of n. What would you expect if you double the length of the input and you got a linear time algorithm? What would you expect the running time to do? What's the ratio of 2n over n? 2. So a linear algorithm the running time should double when you double the length of the input. But merge sort's a little worse than linear. It's n times the small log n term. So it should do a little, what we would expect to see for merge sort is it's a little worse than doubling the time each time you double the size. We're actually, except for, well, it keeps showing us as doing better than linear, which again is an artifact of my sloppy timing. Let's run it again. And more or less the same thing happens. But in a careful experiment, what you would find is that merge sort, the running time a little worse than doubles when you double the length of the input. I want to make sure I didn't make a mistake. I'm going to run the test on it. Yeah, merge sort's correct. This often happens in lecture. My timing results don't look quite right. Now, one final thing, and we'll be done. Let's see. Run this again to see what the numbers are. Why is it not show? I'm running the test. Okay, so this is my merge sort again, and it's not the world's best merge sort. So up at 8 million, it took 1.2 seconds to do. Let's compare that to the built-in sort, the sort that's built into Java. Now, do you think the sort that's built into Java will do better or worse than that merge sort I wrote for you? Better. You better believe it'll do better because they spent some time engineering it. So let's see. Remember, my last time was 1.2 seconds, and their last time is about half that. So if you look at the ratios look like an n log n algorithm, a little worse than doubling in general. And so, yeah, their algorithm is still n log n. You can't do better than that in general. But it's twice as fast because they worked harder at it, and it's not merge sort. I'm not exactly sure what Java sort is, but it's some combination of merge sort and quick sort, a hybrid algorithm. And you'd expect that they put more effort, so they got a faster algorithm. Okay, I'll leave you with one final thought. if you have to choose between using, suppose you've got a choice. You can use insertion sort. You got insertion sort, or you could use quick sort, or you could buy a faster computer. Okay? Which is the bigger payoff? Moving from selection sort to merge to quick sort, or continuing to use insertion selection sort but get a computer that's twice as fast? What's more important, the algorithm or the computer? The algorithm. You could take the crappiest computer from 20 years ago and let it run quick sort, and take my laptop from last year and let it run selection sort on a large array, say millions of elements, and the crappy computer running the good algorithm will blow the faster computer away. Algorithms are incredibly important. Computers double in speed every 18 months, or used to. Algorithms can make revolutionary changes in how fast things work. So just bear that in mind. We are done.